Imagine staring into absolute nothingness. No stars, no space, not even time itself. Our human minds are wired to picture emptiness as a blank black void, but true nothingness is far stranger. In fact, science tells us that what we call nothing has never really been empty at all. At the smallest scales of reality, quantum physics shows us that the so-called void is alive with activity. Particles flicker in and out of existence. Energy hums at the very fabric of spacetime, and probability itself seems to be playing dice in the darkness. And from this restless nothing, somehow, everything we know, galaxies, planets, life, and even your own thoughts, came into being. But that's just the beginning of the mystery, because when we try to trace the universe back to its first instant, to the Big Bang itself, the questions only multiply. What was before the beginning? Was there a before at all? Or did time itself spark into existence in that fiery explosion? These are not just questions for philosophers. Physicists, cosmologists, and mathematicians have spent decades wrestling with them, building theories that often sound more like science fiction than science fact. Some believe our universe was born from a random quantum fluctuation in an ocean of false vacuum. Others think we're only one bubble in an infinite multiverse, colliding with other realities like cosmic soap bubbles in a vast frothing sea. And some go further still, suggesting our entire universe is a kind of hologram, an elaborate projection of information encoded far beyond our reach. If that's true, then the stars, the Earth, and even you may not be as solid as they appear. But the most mind-bending idea of all is that consciousness, your awareness, my awareness, the very act of observing reality, may have played a role in bringing the universe into existence. If that's the case, then the Big Bang wasn't just the start of matter and energy. It was the universe waking up, and every one of us may be part of the reason it continues to exist. And what comes next? That's the question that keeps scientists, dreamers, and seekers awake at night. And the answer may be stranger than anything we've ever dared to imagine. When we peel back the layers of time and look for the earliest possible origins of everything, we run straight into a paradox that has haunted both science and philosophy for centuries, the nature of nothingness. At first glance, nothing should be the simplest concept imaginable, an absence, a void, a complete lack of anything. But the deeper we probe into physics, the stranger that idea becomes, because what looks like emptiness isn't empty at all. In fact, it may be the most energetic and mysterious state of all, holding within it the seeds of universes, including ours. To understand this, we have to start with one of the most confusing yet fascinating ideas of modern physics: quantum fluctuations. In the quantum world, particles do not behave like tiny billiard balls. They are smeared across probabilities, existing in multiple states until measured or observed. Even in what we call a vacuum, pairs of particles and antiparticles constantly blink in and out of existence, appearing for a brief instant and then annihilating each other. To us, this looks like random chaos, but at the level of the universe, it could be the very mechanism that gave birth to everything. Imagine nothingness not as a silent void, but as a roiling, restless ocean of possibility where existence itself is trying to burst through. Physicists call this idea the quantum vacuum, and far from being empty, it is rich with potential energy. Some theorists argue that the Big Bang might have been triggered by one of these fluctuations becoming unstable, releasing its energy in a colossal outpouring that expanded into the universe we now inhabit. This is sometimes described as the universe from nothing, though the nothing in question is not truly nothing. It is more like the most subtle form of something imaginable, a stage where the rules of physics already existed even before matter and time as we know them began. This raises an even deeper question. If those laws of physics were already there, then where did they come from? Are they eternal, existing outside of time, or did they too emerge in the same instant as the universe? This mystery is one of the reasons cosmology is both exhilarating and unsettling, because every answer seems to open up 10 more questions. But quantum fluctuations are not the only idea on the table. Another contender is the concept of a false vacuum, a kind of unstable energy field that could exist throughout space. Picture a ball resting not at the bottom of a valley, but balanced precariously on a hilltop. Eventually, the ball will roll down, and as it does, it releases energy. Some physicists think our universe may have come into being as a result of such a collapse. with the false vacuum decaying into a lower energy state and releasing the energy that fueled the Big Bang. If that's true, then it's possible that other parts of reality, beyond our observable universe, are still trapped in false vacuums, waiting to collapse and create other universes of their own. This leads to the multiverse hypothesis, the possibility that our cosmos is only one bubble in a vast and infinite cosmic foam. From this perspective, universes may constantly be born, live out their existence and fade away, with countless others forming in parallel. We, in this view, just happen to inhabit one bubble where the conditions were right for life to emerge. The unsettling part is that if the multiverse is real, then the Big Bang wasn't unique. It wasn't the beginning of all beginnings, but just the start of our particular story. That realization flips the narrative on its head. Instead of asking, why did the universe exist at all, we might have to ask why this universe with these laws, and with us inside it. And one answer could be as strange as it is humbling. We're here simply because the laws of this particular bubble allow us to be. Had the constants of physics been slightly different, had gravity been weaker, or the strength of atomic forces changed by just a hair, then stars would never have formed, planets would never have taken shape, and no life would have been possible. This idea is called the anthropic principle, and while some scientists dislike it for sounding more philosophical than scientific, it forces us to confront the eerie possibility that our universe is fine-tuned for existence. Or at least for our kind of existence. But if all this is true, then we still circle back to the core enigma. Why does anything exist at all instead of nothing? Some argue that the very question may be flawed because nothing is unstable by nature. The rules of quantum mechanics suggest that emptiness naturally gives rise to something, that true nothingness, in the strictest sense, might be impossible. If so, then perhaps existence is inevitable, not exceptional. This flips our perspective yet again. Maybe the universe isn't a bizarre accident, but the only possible outcome of a reality that cannot remain empty. And here's where philosophy and physics begin to blur, because whether we are talking about quantum laws, false vacuums, or multiverses, we are still searching for the ultimate foundation, the reason those rules exist at all. Some thinkers believe we may never find an answer within science alone, because any explanation we create will always rely on deeper assumptions. At some point, we either accept that the laws of physics just are, or we start entertaining ideas that reach beyond physics altogether. What makes this even more fascinating is how human consciousness gets tangled into the puzzle. In the quantum world, observation seems to play a critical role. Particles behave one way when unobserved and another way when measured. Some interpretations suggest that without observation, the universe might remain in a state of potential, only solidifying into reality once it is perceived. If that's true, then consciousness isn't just a byproduct of the universe, but part of the mechanism that brings it into being. This has led to some startling speculation. Perhaps the universe needs observers in order to exist. If so, then life, intelligence, and awareness are not trivial accidents, but essential components of the cosmos itself. And that ties directly into why so many people feel a deep sense of wonder when confronting these mysteries, because in some sense, we are not separate from the universe's story, but the universe experiencing itself. All of this shows why the beginning of everything remains one of the most captivating and unsolved riddles of human thought. It pushes science to its limits, and forces us to wrestle with concepts that feel more like riddles than answers. Did the universe emerge from a quantum fluctuation, a false vacuum collapse, or a multiverse of infinite bubbles? Or is the truth even stranger, involving ideas of consciousness and reality we can barely grasp? The fact that we can even ask these questions shows how far human curiosity has carried us, from staring at the stars in awe to unraveling the very fabric of existence. Yet for every breakthrough we make, the mystery deepens. And maybe that's the point. The journey itself keeps us moving forward, driven by the hunger to understand where we came from and why there is something rather than nothing. If the origins of the universe force us to wrestle with the idea of something from nothing, then the next great puzzle lies in time itself. Time feels so natural to us. Seconds ticking away on a clock, the sun rising and setting, our own bodies aging, that we rarely stop to question what it really is. Yet when we pull back the curtain, time is anything but simple. It is slippery, relative, and maybe not even fundamental to reality. And when we try to trace time backward toward the moment of the Big Bang, things become even stranger. Because at the ultimate beginning, many physicists believe time itself may not have existed at all. Instead of a universe unfolding across a timeline, there may have been a timeless state, a reality in which before and after had no meaning. That's almost impossible to wrap our minds around, since our entire experience of life depends on the flow of time, but the mathematics of cosmology keep hinting that the arrow of time is not as straightforward as we think. Let's start with Einstein's theory of relativity, which shattered the old idea of time as a universal fixed backdrop. Einstein showed us that time is woven together with space, forming a four-dimensional fabric called spacetime. In this fabric, time stretches and bends depending on speed and gravity. Move close to the speed of light, and time slows for you compared to someone standing still. Stand near a black hole, and gravity distorts time so dramatically that minutes for you could equal thousands of years far away. This means that time is not absolute but relative to perspective, a shocking idea that has been proven again and again by experiments. But relativity also raises a haunting possibility. Maybe past, present, and future all coexist within space-time, like pages in a book. From this perspective, time doesn't flow. Instead, we move through it, experiencing one moment at a time, but all moments already exist. If true, then your birth, your life, and even your death are already etched into the cosmic fabric, just waiting for your consciousness to travel through them. But if time works this way, why do we experience it as moving forward? This is where the concept of entropy, or disorder, comes in. According to the second law of thermodynamics, entropy in a closed system always increases. A cup of hot coffee cools down. It never spontaneously heats back up. A broken glass doesn't reassemble itself. In the universe, entropy gives time its direction, what scientists call the arrow of time. Without entropy, the past and future would be indistinguishable. The problem is, when we look back at the Big Bang, the universe seems to have begun in a state of extremely low entropy, a state of perfect order. And that's baffling. Why should the cosmos have started in such a precise, ordered state when chaos is so much more likely? Some scientists suggest this initial order was a kind of cosmic fine-tuning, the conditions necessary for stars, galaxies, and eventually life to arise. Others think it may hint at deeper laws we haven't yet uncovered. Either way, it raises one of the most profound questions in science. Why was the universe born in a state of such improbable order? Now, here's where things get even stranger. Some cosmologists propose that time itself might be an emergent property, not a fundamental ingredient of reality. In this view, time could arise out of quantum entanglement, the mysterious connection between particles across space. When vast numbers of particles interact, their entanglement might create the illusion of time flowing, even though at the deepest level time doesn't exist at all. If so, our perception of past and future may be nothing more than a construct emerging from the way information is processed in the universe. Think of it like watching a movie. The individual frames already exist on the reel, but our brains interpret them as continuous motion. The universe may work the same way, with our minds weaving the illusion of a flowing timeline from a deeper, timeless reality. Another perspective comes from the concept of cyclical time, an idea found in both ancient philosophies and cutting-edge cosmology. Instead of time stretching infinitely forward in one direction, the universe might pass through endless cycles of birth, death, and rebirth. In this model, the Big Bang was not the absolute beginning, but the latest phase in an eternal cycle. Universes expand, collapse, and begin again, like cosmic phoenixes rising from their own ashes. If this is true, then time has no true beginning or end. It loops eternally, with our current reality just one iteration among countless others. This idea appeals to some because it avoids the thorny problem of a singular first cause, but it also leads to haunting questions. If everything repeats, do our lives repeat as well? Are we destined to relive the same story again and again, or do new variations emerge with each cycle? And then there's the boldest idea of all, that time itself might be an illusion. Some physicists argue that when we push beyond relativity and quantum mechanics toward a theory of everything, time may disappear from the equations altogether. If that's the case, then our sense of moving through moments could be nothing more than a trick of perception, like shadows cast on a wall. This isn't just abstract speculation. Some versions of quantum gravity and string theory suggest that the fundamental description of reality doesn't include time at all. Instead, time may be something our brains impose on reality to make sense of change. That would mean the universe, at its deepest level, is timeless, and our lives are like patterns frozen in an eternal block of existence. It's a chilling thought, but also strangely freeing, because it suggests that nothing is ever truly lost. Every moment we experience may exist forever, locked into the structure of reality itself. Of course, with every attempt to explain time, new contradictions emerge. If time is an illusion, why do we all experience it so consistently? If entropy drives the arrow of time, why did the universe begin in a state of low entropy in the first place? If time is relative and space-time is a block, does free will even exist? Or are we just actors following a script that has already been written? These are the kinds of questions that make scientists hesitate, because they blur the line between physics and philosophy. Yet they're also the kinds of questions that pull us deeper into the mystery. Because if we ever unravel time's true nature, it may unlock answers not only about the universe's past, but also about its future. Whether it will expand forever, collapse into itself, or dissolve into something beyond our comprehension. And here's the haunting twist. Our everyday lives are built on assumptions about time that might not be true. We plan for tomorrow, reminisce about yesterday, and measure our lives in hours and years. Yet if physics is right, tomorrow may already exist, yesterday may never have vanished, and the flow of time may be an illusion altogether. That realization is not just a scientific puzzle, but a deeply human one. It forces us to confront what it means to live, to act, and to make choices in a universe where time may not be what it seems. And perhaps that's why exploring the nature of time matters so much. It's not just about equations or cosmology. It's about understanding the stage on which the entire drama of existence, including our own, plays out. And the closer we look, the less that stage looks like a straight line, and the more it looks like something far stranger, something that may hold the key to everything. If the first great puzzle was the origin of the universe, and the second was the nature of time, then the third mystery pulls us into the invisible framework that holds the cosmos together. A framework we can't see, can't touch, and yet without it, everything would fall apart. This is the realm of dark matter and dark energy, the strange, unseen forces that make up the vast majority of the universe. When we look at the stars and galaxies scattered across the night sky, it feels like we're seeing the fullness of the cosmos. But in reality, all the glowing matter, stars, planets, gas, dust, and everything we've ever directly observed, makes up less than 5% of the universe. The rest is dominated by things we don't understand. Roughly 27% is dark matter, an invisible substance that outweighs ordinary matter and seems to act like a cosmic glue, binding galaxies together. And nearly 70% is dark energy, a force even more mysterious, pushing the universe apart at an ever-accelerating pace. Together, these two enigmas shape the fate of the cosmos, yet they remain among the greatest unsolved questions in science. The story of dark matter begins with a simple observation: galaxies spin too fast. If you calculate the gravitational pull of all the stars in a galaxy, it's not nearly enough to hold the galaxy together. By all logic, the outer stars should be flung into space like riders tossed from a carnival ride spinning out of control. Yet galaxies stay intact, rotating faster than they should, as though held by an unseen hand. In the 1930s, Swiss astronomer Fritz Zwicky noticed this discrepancy while studying galaxy clusters and suggested there must be missing mass holding them together. His idea was dismissed at the time, but decades later, more precise observations confirmed it. The missing mass was real. But here's the catch. It doesn't shine, it doesn't absorb light, it doesn't interact with electromagnetic radiation in any way. That's why we call it dark matter. It is invisible, detectable only through its gravitational effects, like a ghost shaping the dance of galaxies. The search for dark matter has taken us deep underground and into outer space. Scientists have built enormous detectors buried in mines, shielded from cosmic rays, hoping to catch a rare collision between dark matter particles and ordinary matter. Yet so far these detectors have come up empty. Theories abound about what dark matter could be. Exotic particles like WIMPs, weakly interacting massive particles, sterile neutrinos, or even primordial black holes left over from the earliest moments of the universe. Each possibility is tantalizing, but none have been proven. And the longer we search without finding it, the more unsettling the question becomes. What if dark matter isn't a particle at all? What if our very understanding of gravity needs to change? Some physicists argue that instead of adding invisible matter, we may need to modify Einstein's equations of gravity to account for the strange motions of galaxies. But so far no alternative has explained all the evidence as neatly as dark matter does. If dark matter is perplexing, dark energy is downright terrifying. Its discovery in the late 1990s shook the foundations of cosmology. Until then, scientists believed the expansion of the universe, the stretching of space that began with the Big Bang, should be slowing down over time, dragged by the pull of gravity. But when two independent teams measured distant supernovae, they discovered the opposite. The expansion is speeding up. Some unknown force is not only pushing galaxies apart, but doing so with increasing strength. This force was named dark energy, and it makes up the largest component of the universe. But what is it? Some theories suggest it is a property of space itself, a kind of vacuum energy that emerges from the fabric of spacetime. Others imagine a new kind of dynamic field permeating the cosmos dubbed quintessence. And some even speculate it could be a sign that our universe is embedded in a much larger multiverse, with different regions experiencing different laws of physics. The unsettling truth is that no one knows. What makes dark energy especially chilling is its implications for the fate of the universe. If the expansion continues to accelerate indefinitely, galaxies will drift farther and farther apart until billions of years from now, even the closest ones vanish beyond our view. Stars will burn out, black holes will evaporate, and the universe will fade into a cold, dark emptiness, a scenario known as the heat death. But that isn't the only possibility. If dark energy grows stronger over time, it could eventually rip apart not only galaxies but also stars, planets, and even the atoms themselves in a cataclysm called the Big Rip. On the other hand, if dark energy weakens or changes its nature, the universe's expansion might slow down, halt, or even reverse, leading to a big crunch in which everything collapses back into a singularity. Each outcome depends on the true nature of dark energy, a mystery still hidden from us. What makes this mystery even deeper is the way dark matter and dark energy interact with the story of the cosmos itself. Without dark matter, galaxies would never have formed. After the Big Bang, ordinary matter was too hot and energetic to clump together on its own. But dark matter, unaffected by radiation, began pooling into invisible structures called halos. These halos provided the gravitational wells that pulled ordinary matter together, seeding the birth of galaxies and stars. In other words, the very existence of our Milky Way, our Sun, and our Earth may owe itself to this unseen substance. And yet, as galaxies formed and grew, dark energy began to dominate, pushing the universe apart and dictating its large-scale structure. It's as if the cosmos is balanced between two invisible titans, dark matter pulling things together, and dark energy driving them apart. Beyond the scientific puzzles, the existence of dark matter and dark energy raises unsettling philosophical questions. If 95% of the universe is invisible and unknown, what does that say about our place in it? For centuries, humans assumed we were at the center of everything, only to be pushed farther into obscurity, first by Copernicus showing Earth was not the center of the solar system, then by astronomy revealing our sun is just one star in a galaxy among billions. Now we face the most humbling realization yet. Everything we see, from galaxies to atoms to our own bodies, is just a tiny fraction of reality. The universe is dominated by things we cannot see or comprehend, and perhaps most haunting of all is the possibility that we may never fully uncover these mysteries. Dark matter could be forever beyond our reach, interacting so weakly with ordinary matter that no detector will ever capture it. Dark energy could remain a cosmic placeholder, a name for our ignorance rather than a discovery waiting to be made. If so, the greatest forces shaping the universe may remain in the shadows, leaving us to grapple with a reality we can only partially glimpse. Yet it is precisely this mystery that drives science forward. Every unanswered question about dark matter and dark energy pushes us to build better telescopes, design more sensitive detectors, and imagine new theories that stretch the boundaries of physics. And in that sense, the darkness becomes a source of light, because in seeking to understand it, we expand the horizons of human knowledge. The invisible scaffolding of the cosmos may be beyond our sight, but its fingerprints are everywhere, shaping galaxies, guiding stars, and writing the ultimate destiny of the universe. And as long as we keep searching, the unseen will continue to reveal itself, one discovery at a time. If dark matter and dark energy reveal the unseen scaffolding of the universe, then black holes are the places where reality itself seems to tear apart. Few cosmic objects capture the imagination or the fear of humanity as much as black holes. They are regions of space where gravity is so overwhelming that nothing, not even light, can escape. On the surface, that sounds simple, an object with gravity strong enough to trap anything. But the deeper we look, the stranger they become. Black holes don't just bend space, they warp time, twist the fabric of reality, and blur the line between physics and philosophy. They represent the ultimate paradoxes in science, places where Einstein's theory of relativity and the bizarre rules of quantum mechanics collide head-on, leaving us with questions that no theory can fully answer. To understand black holes is to walk up to the very edge of knowledge itself and stare into the abyss. The journey begins with the idea of a singularity, the point at the heart of a black hole where all of its mass is crushed into infinite density. Here the laws of physics as we know them break down completely. General relativity tells us that gravity warps spacetime, but at the singularity spacetime itself collapses into an infinitely small point. Infinity in physics is usually a sign that the theory has reached its limits. It's like the universe is telling us, you don't have the tools to go further. But that hasn't stopped scientists from trying. The singularity remains one of the most perplexing mysteries in all of science. Not just a place where answers end, but a challenge to invent new physics that can reconcile relativity with quantum mechanics. Surrounding the singularity is the event horizon, the point of no return. Cross this invisible boundary and escape becomes impossible. Even if you travelled at the speed of light, you'd never break free. From the outside, the event horizon looks like a dark sphere, perfectly black against the glow of space. But what makes it haunting is what happens as you approach it. Time itself begins to warp. To an outside observer, someone falling toward a black hole appears to slow down, moving slower and slower until they freeze at the event horizon. From their perspective, though, they continue falling, plunging toward the singularity in a matter of seconds. This bizarre distortion of time is a real consequence of relativity, and it reminds us that black holes are not just objects, but places where reality itself bends in ways our minds struggle to comprehend. And then there's the paradox of information. According to the principles of quantum mechanics, information, the fundamental description of particles and their states, can never be destroyed. But if something falls into a black hole, it seems that all information about it is lost forever. Burn a book, and its information is preserved in the smoke, heat, and ash. Toss the same book into a black hole, and it vanishes without a trace. This contradiction between relativity and quantum mechanics is known as the black hole information paradox, and it has tormented physicists for decades. Stephen Hawking once argued that information is destroyed in black holes, a claim that shook the foundations of physics. Later he revised his view, suggesting that information might be encoded on the surface of the event horizon, like a hologram, and slowly leak back out as the black hole evaporates through Hawking radiation. But the problem remains unresolved, and with it, one of the greatest clashes in science. Can the universe both obey relativity and quantum mechanics, or do we need an entirely new theory to explain black holes? Hawking radiation itself adds yet another layer of mystery. In 1974, Hawking proposed that black holes are not truly black. Instead, quantum effects near the event horizon cause them to emit tiny amounts of radiation. Over immense timescales, this radiation causes black holes to lose mass and eventually evaporate entirely. A black hole the mass of a star would take far longer than the current age of the universe to disappear, but smaller black holes, if they exist, could be vanishing right now. The idea that these cosmic monsters are not eternal, but slowly dissolve into nothing, adds a poetic twist. Even the most terrifying objects in the universe eventually fade away. Yet it also complicates the information paradox further, because if black holes evaporate, what happens to the information inside them? Does it vanish, or does it somehow escape with the radiation? No one knows for sure. Black holes are not just theoretical puzzles, they're real, and we've seen their effects across the cosmos. At the heart of nearly every galaxy, including our own Milky Way, lies a supermassive black hole, millions or even billions of times the mass of the Sun. These giants are engines of cosmic power, capable of launching jets of energy that stretch for thousands of light years. In 2019, the Event Horizon Telescope gave us the first direct image of a black hole's shadow, a glowing ring of superheated gas swirling around the abyss in a galaxy 55 million light-years away. That moment was historic, humanity's first glimpse of the unseeable. But it was only the beginning. Every observation of black holes reveals new anomalies, new behaviours that push the limits of our theories. For example, the collision of two black holes, detected through gravitational waves by LIGO in 2015, proved not only that black holes can merge, but also that the ripples they send through spacetime can be detected on Earth. These gravitational waves opened a new window into the universe, letting us hear the final moments of black hole dances that happened billions of years ago. And yet, for all we've discovered, black holes remain the most mysterious objects in existence. They blur the line between science and philosophy, between reality and imagination. Some theorists suggest that inside black holes might lie gateways to other universes, wormholes connecting distant regions of spacetime. Others imagine that black holes could be the seeds of new universes themselves, with each singularity birthing a new cosmos beyond our reach. These ideas may sound like science fiction, but they emerge from the same mathematics that gave us relativity and quantum mechanics. And perhaps that's what makes black holes so captivating. They remind us that the universe is not bound by our common sense, that the rules we take for granted can shatter in the most extreme corners of reality. Ultimately, black holes are less about destruction and more about revelation. They reveal the fragility of our theories, the limits of our knowledge, and the vastness of the unknown. They show us that the universe is not a simple machine running on predictable gears, but a place where the deepest mysteries remain unsolved. To study black holes is to admit that we are still children in a cosmic library, peeking at the first few pages while infinite volumes stretch beyond our sight. And maybe that's the most powerful lesson of all, that the universe still holds secrets so profound, so alien, that even the brightest minds cannot yet decipher them. In their silence, in their darkness, black holes whisper a truth we cannot ignore, that reality itself is stranger than we can imagine, and the closer we look, the stranger it becomes. If black holes represent the terrifying extremes of destruction, then exoplanets embody the tantalizing extremes of possibility. They are the worlds beyond our solar system, planets orbiting distant stars that until a few decades ago we had no evidence even existed. For centuries, philosophers and dreamers speculated about other worlds, from Giordano Bruno, who dared to imagine innumerable suns with innumerable Earths, to science fiction writers who filled our imaginations with alien landscapes. But it wasn't until 1992 that astronomers confirmed the first exoplanets, and since then the discoveries have exploded. Today, we know of more than 5,000 confirmed exoplanets, and each new detection reveals a cosmos far stranger, wilder, and more varied than we ever imagined. These worlds don't just challenge our expectations, they shatter them, forcing us to rethink what a planet can be, what life might need to survive, and even whether Earth is as unique as we once thought. The most astonishing revelation is how bizarre these alien worlds are compared to our familiar solar system. Some exoplanets, called hot Jupiters, are gas giants orbiting so close to their stars that their years last only a few days, their atmospheres boiling under unimaginable heat. Others are super-Earths, rocky planets larger than our own but smaller than Neptune, with surface gravities that could crush us yet possibly harbour oceans deeper than anything on Earth. Some worlds appear to rain molten glass, with winds that hurl shards sideways at thousands of miles per hour. Others are tidally locked, with one side baked in eternal daylight and the other frozen in perpetual night, creating a twilight band where strange climates could emerge. There are planets orbiting pulsars, the remnants of dead stars bathed in radiation yet somehow clinging to existence. And then there are rogue planets, entire worlds drifting alone through the darkness, ejected from their star systems, wandering the interstellar void without a sun to warm them. What makes these discoveries even more thrilling is the fact that some of these planets may be habitable. The habitable zone, the region around a star where liquid water could exist, is no longer a concept we apply only to Earth. Many exoplanets orbit within these zones, raising the possibility that life could exist in conditions radically different from our own. Planets around red dwarf stars, for instance, are bathed in dim, reddish light, with stellar flares blasting their atmospheres. Could life survive there, evolving under a scarlet sun? Some astronomers believe it's possible. In fact, because red dwarfs are the most common stars in the galaxy, the majority of habitable zone exoplanets may orbit them. This means that the most likely homes for alien life could be places that look nothing like our sunny blue Earth. The technology driving these discoveries has advanced at an astonishing pace. The Kepler Space Telescope, launched in 2009, revolutionized exoplanet science by staring at a single patch of sky and measuring tiny dips in starlight caused by planets passing in front of their stars. Kepler revealed that planets are everywhere, far more common than we ever dared hope. Almost every star in the night sky likely has at least one planet, and many may have entire families of them, just like our solar system. The discovery rate has only accelerated with the Transiting Exoplanet Survey satellite, TS, and most recently the James Webb Space Telescope, JWST. Webb is not just detecting planets, it's analysing their atmospheres. Already, JWST has detected water vapour, carbon dioxide, methane, and even possible hints of strange molecules that may point toward exotic chemistry. While none of these detections prove the existence of life, they are the first steps in what could become the most profound discovery in history, the detection of biosignatures on another world. But the search for life also forces us to confront difficult questions. What if life out there doesn't resemble life here? We assume life needs liquid water, carbon-based chemistry, and Earth-like conditions, but that may just be a reflection of our own biases. Could there be life in methane oceans, like those on Saturn's moon Titan? Could organisms survive in the crushing atmospheres of super-Earths, or the frozen crusts of rogue planets heated by internal radioactive decay? The possibilities are staggering, and every new discovery expands the boundaries of our imagination. Exoplanets teach us that habitability is not a single box to be checked, but a spectrum of possibilities, some of which may look utterly alien to us. Exoplanets also challenge us with a sobering perspective. Earth may not be as special as we think. For centuries, our planet has seemed like a rare jewel, the only world with liquid water, continents, and life. But now we know that planets are common, water is widespread, and the ingredients for life are scattered across the galaxy. This doesn't diminish Earth's uniqueness. Instead, it forces us to see our world as part of a larger cosmic tapestry. Perhaps there are millions of Earth-like planets orbiting distant stars, some older and more advanced, some younger, and just beginning their journeys. The question is no longer, are we alone, but how many others are out there, and what might they be like? The implications for humanity are enormous. The discovery of habitable exoplanets reshapes our place in the cosmos. It suggests that life is not a fluke but a natural outcome of physics and chemistry, a process that could repeat across billions of worlds. And if life is common, then intelligence might be too, raising the tantalizing and sometimes unsettling possibility that we are not the only thinking beings in the galaxy. The search for exoplanets is not just about finding alien oceans or exotic atmospheres. It's about confronting the possibility of cosmic neighbours, some of whom may be looking back at us with the same curiosity and wonder. But perhaps the most awe-inspiring part of exoplanet science is how it stirs our imagination. Each new world discovered is like a story waiting to be told, a stage set for adventures we can barely imagine. A lava world locked in eternal fire, a frozen planet with hidden oceans beneath its ice, a super-Earth where mountains rise 3 times taller than Everest. These are not just scientific curiosities, they are reminders of how vast and creative the universe is. And as technology advances, we may one day send probes, or even people, to explore these alien realms firsthand. The dream of interstellar travel may still be centuries away, but every exoplanet discovered is a promise that there are destinations worth reaching. In the end, exoplanets remind us of both our smallness and our potential. We are just one planet among countless billions, orbiting an ordinary star in an ordinary galaxy. Yet from our small corner of the cosmos, we are beginning to map the worlds of the stars. Each discovery pushes us closer to answering the most profound question of all: are we alone, or is life a universal story written across the galaxy? And as we ask that question, we're also writing our own story. One of curiosity, exploration, and the courage to seek out the unknown. Because in the search for other worlds, we are ultimately discovering ourselves, our future, and our place in the vast, mysterious universe. If exoplanets open the door to the possibility of life beyond Earth, then the next logical step is to ask the haunting question: if the universe is filled with so many worlds, why haven't we encountered anyone yet? This is the heart of what's known as the Fermi paradox, a puzzle that has captivated and unsettled scientists, philosophers, and ordinary people alike. On one hand, the numbers suggest life should be common. There are an estimated 200 billion stars in our galaxy, and likely more planets than stars. If even a small fraction of those planets are habitable, and if life emerges naturally when conditions are right, then the galaxy should be teeming with living worlds. Some of those civilizations could be millions of years older than us, with technology far beyond our comprehension. By now, they should have colonized the galaxy, built megastructures, or at the very least left detectable signals. And yet, as far as we can tell, the universe is silent. This eerie silence is what keeps scientists up at night. The overwhelming odds in favor of extraterrestrial civilizations contrasted with the complete lack of evidence for their existence. The Fermi paradox is not just a scientific curiosity. It strikes at the core of humanity's place in the cosmos. If we are alone, then Earth carries an unimaginable responsibility as the sole cradle of consciousness in the galaxy. If we are not alone, then where is everyone, and why haven't they revealed themselves? There are countless proposed answers, each more unsettling than the last. One possibility is that intelligent life is rare. Maybe simple life, like bacteria, is common, but the leap to complex technological civilizations is incredibly difficult. Earth's own history seems to support this idea. For billions of years, life remained microscopic, and only in the last 500 million years did complex multicellular organisms flourish. Intelligence capable of technology has existed for only a tiny fraction of that time. If the same holds true elsewhere, then the odds of intelligent life emerging may be vanishingly small. But rarity is only one explanation. Another possibility is that civilizations tend to destroy themselves. Technology is a double-edged sword. It allows civilizations to expand, communicate, and manipulate their environment, but it also gives them the tools for self-destruction. Nuclear weapons, ecological collapse, artificial intelligence run amok. These are just some of the dangers we face as a species. Perhaps the reason we see no evidence of galactic empires is because civilizations rarely survive long enough to reach that stage. This concept is sometimes called the Great Filter, a stage in evolution that is nearly impossible to pass. The Great Filter might lie behind us, meaning life on Earth has already beaten the odds and humanity is unique. Or it could lie ahead of us, meaning our greatest challenges are yet to come and survival is not guaranteed. Either way, it's a chilling thought. Other explanations shift the problem away from rarity or self-destruction and suggest instead that advanced civilizations may deliberately hide. Imagine a galaxy filled with intelligent species, but none of them broadcasting signals or building massive structures because they fear drawing attention. This is the dark forest hypothesis, named after the idea that the galaxy is like a dark forest filled with hunters. In such a forest, the safest strategy is silence, because any noise could reveal your position to a predator. If this is true, then perhaps advanced civilizations are out there, watching us, but they remain hidden out of caution. And if that's the case, then our own attempts to broadcast messages into space, like the Arecibo message or the Voyager Golden Records, might be dangerously naive, like shouting in a dark forest without knowing who is listening. Then there's the possibility that civilizations are out there, but we simply can't recognize their signals. We assume alien technology would be similar to ours, using radio waves or visible light, But what if their communication methods are so advanced that we can't even detect them? Imagine trying to explain Wi-Fi to someone from the Middle Ages. To them, invisible signals carrying information through the air would sound like magic. Perhaps aliens use methods of communication beyond our comprehension. Quantum entanglement, neutrino beams, or something even stranger. In that case, the universe could be buzzing with signals, and we are like ants oblivious to the internet passing over our heads. Another possibility is that civilizations exist but are too far away. The universe is vast beyond imagination, and even at light speed it would take tens of thousands of years to cross the galaxy. If civilizations are separated by such immense distances, they may never encounter each other, or their signals may take so long to travel that by the time they arrive, the civilization that sent them has already vanished. The finite speed of light creates a natural barrier, turning the galaxy into a series of isolated islands. In this view, the silence we experience is not because no one else is out there, but because the distances are simply too great for contact. And yet, despite the silence, there have been tantalizing hints that keep the question alive. Strange radio signals like the famous WOW signal detected in 1977 sparked excitement but remain unexplained. Observations of certain stars have revealed bizarre dimming patterns, leading some to speculate about the existence of alien megastructures, like Dyson spheres designed to harness a star's energy. While natural explanations have usually won out, the fact that these possibilities are even on the table shows how seriously scientists consider the search for extraterrestrial intelligence. Projects like SETI, Search for Extraterrestrial Intelligence, continue to scan the skies, while newer initiatives like Breakthrough Listen use powerful telescopes to search for signs of alien technology. The Fermi paradox also forces us to confront profound philosophical questions. If we are truly alone, does that make humanity's existence more precious, a singular spark of consciousness in an otherwise lifeless galaxy? Or does it make our situation more precarious, as the sole guardians of intelligence in a hostile universe? On the other hand, if we are not alone, then the silence may be even more ominous. Are others ignoring us? Or worse, are they watching us without revealing themselves? Each possibility carries its own weight, reshaping how we think about ourselves and our place in the cosmos. What makes the Fermi paradox so powerful is not that it offers answers, but that it sharpens the questions. It pushes us to explore, to listen, to search, and to imagine. Every exoplanet discovered, every new telescope launched, and every signal scanned brings us closer to confronting the truth, whatever it may be. Perhaps one day we will detect a faint transmission from a distant world, or perhaps we will build ships capable of travelling to other stars and finding silence. Either way, the paradox will continue to guide us, reminding us that the universe is far larger, stranger, and more mysterious than we ever imagined. And maybe, just maybe, the silence itself is the message. Maybe the universe is telling us that survival requires wisdom, caution, and patience, that civilizations which endure do not shout into the void, but learn to live quietly, humbly, and sustainably. If that's the lesson, then the paradox is not just a cosmic riddle, but a warning for us. Because in the end, the question of where is everyone is also a reflection of, will we last long enough to join them? If the universe is teeming with worlds and possibilities, then the question naturally arises, could we ever reach them? Interstellar travel has fascinated humanity for centuries, from the dreams of science fiction writers to the cutting-edge designs of aerospace engineers. Yet, as captivating as the idea is, the practical challenges are immense, almost inconceivable. The nearest star to our solar system, Proxima Centauri, is more than 4 light-years away, roughly 25 trillion miles. Travelling at the speed of modern spacecraft, it would take tens of thousands of years to arrive. Even reaching a fraction of light speed requires energy and technology far beyond our current capabilities. The obstacles are not merely technological, but also physical, biological, and logistical. Time dilation, cosmic radiation, and the immense energy requirements create a scenario that forces us to confront the limits of both physics and imagination. Yet despite these staggering barriers, humanity continues to dream, to calculate, and to theorize about how we might one day cross the gulf between the stars. One of the most well-known theoretical concepts is the idea of a warp drive, popularized in science fiction but also seriously considered by physicists. The principle is deceptively simple in concept. Instead of moving a spaceship through space faster than light, which is impossible according to Einstein's relativity, a warp drive would manipulate spacetime itself. By contracting space in front of the ship and expanding it behind, the ship could effectively travel faster than light without locally breaking the cosmic speed limit. In theory, this would allow journeys to distant stars in a matter of years or decades rather than millennia. The most famous proposal, the Alcubierre drive, demonstrates that the equations of general relativity permit such a phenomenon. But the practical challenges are staggering. Creating a warp bubble requires enormous amounts of negative energy, a substance that may not even exist in usable quantities. Stabilizing the bubble, navigating safely and protecting the spacecraft from relativistic hazards all remain unsolved problems. Yet the very possibility that spacetime itself can be shaped to facilitate travel is enough to keep theoretical physicists awake at night, calculating, hypothesizing, and dreaming. Another tantalizing approach is the concept of generation ships, enormous spacecraft designed to house multiple generations of humans as they journey to distant stars. In this scenario, crews would live, reproduce, and die aboard the ship over hundreds or thousands of years before reaching their destination. This idea solves the problem of travel time without requiring faster-than-light physics, but it introduces an entirely different set of challenges. A self-sustaining biosphere would need to be maintained for centuries, with food, air, water, and energy recycled flawlessly. Social, psychological, and cultural stability would be critical. Conflicts or breakdowns could doom the mission. The generation ship scenario is daunting, but it is grounded in the laws of known physics, making it perhaps the most realistic path for humanity to explore other star systems in the foreseeable future. Cryogenic suspension or space hibernation offers yet another avenue. If humans could be safely frozen for decades or centuries, interstellar travel might become feasible without requiring multiple generations to live aboard a ship. Advances in cryobiology and life support technology hint at this possibility, though it is far from reality. Long-term human hibernation would require solving the problems of tissue preservation, neural protection, and metabolic management. Even small errors could have catastrophic consequences. Yet, the allure is undeniable, a future where astronauts drift through the stars in suspended animation, waking only when their destination is reached, bridging the unimaginable distances between solar systems. Beyond human-centered solutions, robotic and AI-driven probes represent a more immediate path to the stars. Lightweight spacecraft, potentially accelerated by powerful lasers or electromagnetic drives, could reach nearby stars within decades. Projects like Breakthrough Starshot envision fleets of tiny, wafer-thin probes, pushed by ground-based lasers to a significant fraction of light speed. These probes could capture images, analyze atmospheres, and relay data back to Earth, allowing us to explore distant worlds without sending humans. While such missions won't allow personal experience, they would fundamentally expand our understanding of the galaxy, proving that even in a universe vast beyond comprehension, exploration is possible with ingenuity and determination. However, interstellar travel is not just a matter of physics and engineering, it is also a matter of philosophy, psychology, and ethics. If a civilization spreads to other star systems, what responsibilities do they carry? Colonization raises questions about the treatment of potential alien life forms, the alteration of pristine worlds, and the long-term consequences of expansion. It also forces humanity to confront its own survival. Is interstellar colonization a necessary insurance policy against planetary catastrophe? Or is it an impulsive act that risks repeating the mistakes we've made on Earth on a cosmic scale? These are questions that go beyond equations and spacecraft design, challenging us to consider the moral and existential dimensions of becoming a spacefaring species. Another major hurdle is the relativistic nature of space travel. As a ship approaches significant fractions of light speed, time dilation becomes significant. Travelers may experience years or decades aboard the vessel, while centuries or millennia pass back on Earth. This creates profound implications for human culture and society. Generations may grow up, live, and die on a spacecraft, disconnected from the home planet. News, communication, and history would lag behind reality by centuries. The psychological and societal impact of such isolation is difficult to model, yet it is a necessary consideration for any serious interstellar mission. And then there are the hazards of the cosmos itself. At high velocities, even microscopic particles can cause catastrophic damage. Cosmic rays and radiation pose a constant threat, requiring shielding far beyond what we currently possess. Navigating through interstellar space involves avoiding rogue asteroids, debris, and regions of intense radiation. Any mission, especially one lasting decades or centuries, must be prepared for contingencies that we can scarcely predict. The challenges are immense, but they are not insurmountable. The universe rewards audacity, and for those willing to tackle its extremes, the potential discoveries are beyond imagining. Finally, interstellar travel challenges our very conception of what it means to be human. It forces us to consider not just survival, but adaptation, how humans might evolve to endure new environments, how societies might function in isolation for centuries, and how consciousness itself might be shaped by the vastness of space. Will we send our biology unchanged, or will we merge with technology to transcend our current limitations? Will artificial intelligence precede us, exploring and preparing the galaxy for our arrival? Every solution involves a fundamental rethinking of identity, purpose, and the role of humanity in the cosmos. In the end, the pursuit of interstellar travel is more than an engineering challenge. It is an expression of the deepest human instincts, curiosity, ambition, and the drive to explore. Even when faced with obstacles that seem insurmountable, we continue to imagine, design, and plan for a future in which the stars are not merely points of light but destinations. The journey to other worlds may be centuries or millennia away, and it may require ingenuity we have yet to conceive. But the very act of striving, of turning our eyes and minds to the stars, ensures that humanity remains part of the universe's grand narrative. The obstacles are vast, the distances unimaginable, yet the dream endures, a dream as infinite as the cosmos itself. If interstellar travel stretches the limits of human ambition, then the deeper mysteries of the universe stretch the limits of human imagination itself. Beyond the stars, beyond the galaxies, and beyond even the reach of our most advanced telescopes lie phenomena that challenge the very nature of reality, hidden dimensions, warped space-time, and a cosmos that may be far stranger than we dare to conceive. Modern physics suggests that the universe we see, the familiar 3 dimensions of space and one of time, may be just a fraction of a far more complex structure. String theory, one of the leading candidates for a theory of everything, proposes that the fundamental constituents of reality are not particles, but tiny, vibrating strings. These strings oscillate in multiple dimensions, some of which are compactified, curled up so tightly that we cannot perceive them. The universe may contain 10, 11, or even more dimensions, hidden beyond the veil of perception, shaping the behavior of matter, energy, and gravity in ways that are only beginning to be understood. The concept of hidden dimensions is not merely a mathematical curiosity. It provides potential solutions to some of the deepest problems in physics. For instance, one of the long-standing mysteries is why gravity is so weak compared to other fundamental forces. An electron's electromagnetic interaction is vastly stronger than the gravitational pull it experiences. If extra dimensions exist, gravity might leak into these unseen dimensions, diluting its apparent strength in our observable universe. In this framework, the universe we inhabit is a 4-dimensional brain, floating within a higher dimensional bulk. Our senses perceive only the brain, but other dimensions may contain entirely different realities, parallel spaces where physics and matter behave in ways that seem alien to us. These hidden dimensions also open the door to extraordinary possibilities, including wormholes, tunnels connecting distant points in space and time. If space-time can be warped and shaped, it might be possible, at least theoretically, to traverse cosmic distances instantaneously. Wormholes remain purely speculative, and their creation or stabilization would require exotic forms of matter with negative energy, but the equations allow for the possibility. Such constructs could, in theory, provide shortcuts between galaxies, or even between universes in a multiverse scenario. They challenge our intuitive understanding of distance, making the universe feel simultaneously vast and intimately connected. Brains themselves add another layer of complexity. In some models of string theory, our universe is not the only brain in existence. Multiple brains may float in higher dimensional space, each with its own unique laws of physics. Collisions between brains could explain events like the Big Bang, with the energy released creating a universe in a violent birth. This leads to a startling perspective. Our cosmos may not be a singular creation, but one in an endless series of universes, each emerging from the interactions of hidden dimensions beyond our perception. In this view, the universe is not just vast, it is potentially infinite in ways we can scarcely comprehend. The implications of hidden dimensions are not confined to cosmology. They reach into the realm of particle physics, offering potential explanations for the elusive nature of dark matter and dark energy. If extra dimensions exist, they could host particles that interact only weakly with our familiar matter, appearing as dark matter in our experiments. Likewise, energy associated with the geometry of extra dimensions might manifest as dark energy, driving the accelerated expansion of the universe. In this sense, the hidden structure of the cosmos could be intimately tied to the phenomena that dominate its mass-energy content, revealing that the visible universe is merely the tip of a far more complex iceberg. But with these possibilities come mind-bending paradoxes. If hidden dimensions are real, then our universe may be one among countless others, each shaped by different physical laws. In some universes, stars may never form, or life may take forms inconceivable to us. In others, the fundamental constants may prevent atoms from existing, or create exotic chemistry that defies Earth-based intuition. The multiverse concept transforms the cosmos from a singular entity into a boundless landscape of potential realities, where our familiar world is just one island in an infinite archipelago of possibilities. Even more staggering is the notion that these hidden dimensions might influence our own existence in subtle, undetectable ways. Vibrations in extra dimensions could affect the masses of particles, the strength of forces, or the evolution of galaxies. They might determine whether stars burn steadily or collapse prematurely, whether planets form in stable orbits, or whether conditions suitable for life emerge at all. In this sense, the hidden architecture of reality may govern not only the cosmos but also the very circumstances that allow our existence, embedding life within a web of complexity beyond imagination. The search for evidence of hidden dimensions is underway, though it remains profoundly challenging. Experiments at particle colliders like the Large Hadron Collider aim to detect tiny deviations in particle behavior that could hint at extra dimensions. High-precision measurements of gravity at microscopic scales look for anomalies that might suggest gravitational leakage into unseen realms. Observations of cosmic microwave background radiation and the distribution of galaxies also provide clues, as subtle patterns may reflect the influence of dimensions beyond our perception. Each piece of data nudges us closer to understanding whether our universe is truly solitary or part of a grander multidimensional reality. Philosophically, the idea of hidden dimensions challenges everything we take for granted about existence. It questions our perception of space, time, and reality itself. What we see may be only a fraction of what exists. What we experience may be shaped by influences we cannot perceive. The universe becomes not just vast, but layered, with each hidden dimension adding complexity and depth to the cosmic narrative. It suggests that our familiar reality, the one we navigate day by day, is a projection, a slice of something infinitely more intricate and profound. Ultimately, hidden dimensions expand the frontier of human curiosity. They force us to rethink the nature of reality, to imagine a universe far stranger than our senses reveal, and to embrace the possibility that everything we know is part of a deeper, more complex tapestry. They connect the mysteries of particle physics, cosmology, and even consciousness, hinting at a universe that is alive with structure, possibility, and untold secrets. And as we probe these frontiers, through mathematics, observation, and imagination, we are reminded that the universe is not simply a stage for life and matter, but a boundless canvas of possibility, stretching beyond comprehension, where each discovery unveils further mysteries, and where the unknown is limited only by the reach of our imagination. If hidden dimensions stretch the boundaries of what the universe could be, then the next frontier challenges what the universe actually is. The holographic principle, a concept born from black hole physics and string theory, suggests a reality so strange that it defies ordinary intuition. The universe we perceive as three-dimensional may in fact be a projection, a kind of cosmic hologram encoded on a distant two-dimensional boundary. This idea emerged from attempts to reconcile the mysteries of black holes with the laws of quantum mechanics. In the 1970s, Stephen Hawking shocked the scientific world by proposing that black holes are not entirely black, but emit radiation. This revelation introduced the troubling notion that information about matter falling into a black hole could be destroyed, violating the fundamental principle of quantum mechanics that information can never be lost. To resolve this paradox, physicists developed the idea that information about everything inside a black hole might be stored on its event horizon, encoded in a two-dimensional form. If this is true for black holes, perhaps the same principle applies to the entire universe. The implications are staggering. Imagine the cosmos not as a vast three-dimensional expanse, but as a projection from information encoded on a distant surface. In this scenario, all the matter, energy, and space we experience are effectively shadows of deeper, fundamental information. Just as a hologram on a credit card appears three-dimensional even though it is printed on a flat surface, the universe could have depth and structure that is a consequence of underlying information rather than tangible substance. This challenges everything we consider real. The planets, stars, and galaxies may not be solid objects in the conventional sense, but emergent phenomena arising from the mathematical rules of information stored elsewhere. The familiar solidity of our experience, the ground beneath our feet, the air we breathe, the light of the sun, might all be emergent, encoded features of a deeper, more abstract reality. The holographic principle also offers potential solutions to other cosmic puzzles. Consider gravity. In conventional physics, gravity is an inherent force, an attraction between masses mediated by the curvature of spacetime. But in a holographic framework, gravity could emerge from the information encoded on the boundary of space. Changes in the information could manifest as the gravitational effects we observe, meaning gravity might not be a fundamental force at all, but a consequence of deeper informational processes. Similarly, this perspective may shed light on the enigmatic dark energy accelerating cosmic expansion. Perhaps dark energy is not a mysterious substance permeating space, but an effect arising from the way information is structured across the universe. Quantum mechanics, with its paradoxical superpositions and probabilistic outcomes, gains a new interpretation under the holographic principle. Particles exist in multiple states until measured, and entanglement allows them to instantaneously affect each other across vast distances. In a holographic universe, these peculiarities could be natural consequences of an underlying informational code. The apparent randomness and non-locality of quantum mechanics might reflect the discrete rules of a cosmic program, projected as the three-dimensional universe we experience. What seems chaotic or mysterious at our level could be perfectly orderly at the foundational informational level, obeying rules that we have yet to fully decipher. Beyond physics, the holographic principle has profound philosophical implications. If reality is emergent from information, then what we perceive as space and time is not fundamental. The past, present, and future could be encoded in a timeless informational structure, much like frames of a film reel waiting to be played. Consciousness, which interacts with and interprets this projection, becomes a critical element. Observers might not simply perceive reality, they may participate in shaping it. Some interpretations of quantum mechanics already suggest that observation collapses superpositions into definite outcomes, and in a holographic universe, this act of measurement could be more than passive observation. It could be a way consciousness interacts with the underlying code to generate the reality we experience. This concept also forces us to reconsider the notion of distance and space. If the universe is a projection from information on a distant boundary, the vast separations we perceive may be illusory in some sense. 2 points that appear light years apart in our three-dimensional projection could be closely linked in the underlying informational structure. Entangled particles, which seem to instantaneously influence each other across space, may exemplify this principle. The holographic framework suggests that non-locality is natural, and the universe may be far more interconnected at a fundamental level than our senses reveal. Moreover, the holographic principle implies a limit to information in a given region of space. Just as a computer screen can display only so many pixels, the amount of information within a volume of space is finite and proportional to the area of its boundary, not its volume. This is counterintuitive. We think of a cube of space as containing as much information as its interior, but according to the holographic principle, the true informational content scales with surface area. This insight comes directly from black hole physics, where the entropy of a black hole, a measure of its informational content, is proportional to the area of its event horizon. Extrapolating this to the universe suggests that the cosmos itself has a finite informational capacity, encoded not within its volume but on its outer horizon. The ramifications for our understanding of existence are profound. If the universe is a hologram, the ultimate nature of reality may be entirely abstract, based on information and mathematics rather than tangible matter. The laws of physics, constants, and the behaviors of particles are expressions of encoded data rather than intrinsic properties. Space and time are emergent features, and matter is a manifestation of information. Conscious beings, capable of interacting with this data, may not simply live in the universe, but participate in its unfolding, a co-creation of reality itself. Yet despite its abstraction, the holographic principle is testable. Scientists are devising experiments to detect subtle pixelation or quantum noise in spacetime that could reveal the universe's underlying informational structure. Observations of the cosmic microwave background, gravitational waves, and particle interactions may yield clues that hint at a deeper holographic reality. If verified, these experiments could revolutionize not only physics, but our understanding of existence, merging cosmology, quantum mechanics, and information theory into a unified vision of the cosmos. Ultimately, the holographic principle invites us to view reality in a way that is simultaneously humbling and exhilarating. It suggests that the solidity and continuity we take for granted may be illusions, and that the true substance of the universe lies in patterns of information encoded beyond our perception. It challenges our notions of space, time, matter, and consciousness, revealing a cosmos more intricate and interconnected than we have ever imagined. And in confronting this vision, we're reminded that the universe is not merely a backdrop for our existence, but a complex, layered tapestry, one whose deepest truths remain tantalizingly just out of reach, waiting for our curiosity, ingenuity, and imagination to unveil. If the universe is a holographic projection, filled with hidden dimensions and governed by deep informational rules, then one of the most profound questions emerges. How does life arise in such a cosmos, and what is the nature of consciousness itself? Life is not merely a chemical accident, but a phenomenon that bridges physics, chemistry, and information theory in ways that remain mysterious. The origin of life on Earth, the process by which non-living matter organized into self-replicating, metabolizing organisms, remains one of the most tantalizing puzzles in science. From the primordial soup of simple molecules, life somehow emerged, exploiting energy gradients, forming complex polymers, and eventually creating the first cells. Yet despite decades of research, the precise mechanisms remain elusive, and when we expand our view to the cosmos at large, the questions multiply. If life arose here, how likely is it to arise elsewhere, and under what conditions? Recent research suggests that the conditions for life may not be as rare as once thought. Amino acids, the building blocks of proteins, have been detected on comets and in interstellar clouds, indicating that some of the basic ingredients for life are widespread in the galaxy. Nucleotides, essential for DNA and RNA, may also form under certain cosmic conditions. This raises the possibility that the seeds of life, organic molecules, chemical precursors, and energy sources, are scattered throughout the cosmos, waiting for the right environments to assemble into living systems, and yet the jump from molecules to self-replicating organisms remains vast. Life is not merely chemistry, it is organized complexity, a network of reactions that maintain themselves far from equilibrium, constantly processing energy and information to sustain existence. Consciousness takes this mystery to an even higher level. While life can exist without awareness, consciousness introduces self-reflection, intentionality, and subjective experience. It is one of the greatest enigmas in science because it is not simply an emergent property of matter. It interacts with reality in ways that are deeply puzzling. Neuroscience has made strides in mapping brain activity and understanding the mechanisms of perception, cognition, and decision-making, but the hard problem of consciousness, why and how subjective experience arises, remains unsolved. Some theorists suggest that consciousness may be fundamental, an intrinsic property of the universe, rather than merely a product of complex brains. In this view, the universe itself may possess proto-conscious qualities, and life may be one way in which the cosmos becomes aware of itself. This idea is not merely philosophical speculation. It intersects with physics and cosmology. Quantum mechanics introduces phenomena that seem to tie observation to reality. In the quantum world, particles exist in superpositions of states until measured, at which point their wave functions collapse into definite outcomes. Some interpretations propose that consciousness plays a role in this collapse, suggesting that awareness is not just a passive observer, but an active participant in shaping reality. While highly debated, these ideas blur the line between physics and consciousness, implying that life may be intimately connected to the fundamental structure of the universe. The emergence of life also illustrates the remarkable fine-tuning of the cosmos. Physical constants, such as the strength of gravity, the electromagnetic force, and the ratio of protons to electrons, must lie within narrow ranges for stable chemistry, star formation, and planetary systems to occur. Even minor deviations could prevent the formation of elements essential for life. Some scientists interpret this fine-tuning through the lens of the anthropic principle. The universe appears precisely configured for life, because only such a universe can contain observers capable of noticing it. Others suggest that we may live in one of countless universes in a multiverse, with many universes having conditions unsuitable for life, making ours an exceptionally lucky bubble. Either way, the delicate balance of physical laws underscores the extraordinary conditions required for life and consciousness to emerge. The interplay between life, evolution, and intelligence adds another layer of complexity. Evolution by natural selection drives organisms to adapt to their environments, creating diversity, resilience, and complexity over time. Yet intelligence, particularly human-level intelligence, is rare even on Earth. It is the result of a series of improbable events, environmental pressures, and genetic mutations spanning billions of years. This raises questions about the likelihood of intelligent life elsewhere. If intelligent civilizations do emerge, what paths might they follow? Some may develop technology that allows them to manipulate their environments on a planetary scale. Others may remain close to biological limits, never reaching the capability to communicate across interstellar distances. This diversity complicates attempts to understand life in the cosmos, and contributes to paradoxes like the Fermi paradox, which asks why we see no evidence of extraterrestrial intelligence despite the seeming abundance of habitable worlds. Consciousness also plays a role in shaping the universe in subtle, potentially profound ways. Human activity, from agriculture to technology, has transformed the biosphere, altered planetary chemistry, and even impacted climate. Intelligence and awareness have consequences beyond the individual, shaping the environment and indirectly the course of evolution itself. If intelligence is not unique to humans, then other conscious civilizations may similarly influence their worlds, leading to a cosmos that is not passive but dynamically intertwined with the beings inhabiting it. In this sense, life and consciousness are not merely passengers in the universe. They are agents that interact with, and perhaps even shape, cosmic processes. Another compelling perspective comes from the concept of self-organizing systems. Life is an example of matter spontaneously organizing into patterns capable of sustaining and reproducing themselves. These systems follow rules that emerge from the fundamental laws of physics, but exhibit behaviors that are not predictable from those laws alone. Complexity arises naturally in systems far from equilibrium, and life may be the most sophisticated expression of this principle. From this viewpoint, consciousness and intelligence are not accidents, but emergent properties of a universe inclined toward complexity. The universe, in a sense, becomes a laboratory in which matter experiments with organization, information processing, and awareness. The potential universality of life and consciousness also forces us to reconsider our place in the cosmos. If life emerges wherever conditions allow, and if consciousness is an emergent property of complex systems, then the universe may be teeming with sentient beings, each experiencing their own realities their own perception of space and time, the implications are staggering. Our experiences, our histories, and our cultures may be one thread in a vast, interconnected web of awareness stretching across galaxies and possibly beyond. Humanity's exploration of the cosmos, through telescopes, probes, and theoretical physics, may be the first step toward understanding this broader tapestry. Finally, the emergence of life and consciousness highlights the intimate relationship between physics and meaning. The laws of nature provide the framework, but it is life that interprets, experiences, and transforms those laws into phenomena with purpose, survival, and awareness. From the simplest microbe to the complexity of human civilization, consciousness allows the universe to reflect upon itself, to observe, question, and wonder. In this sense, life is not merely a biological accident, but a fundamental feature of a universe capable of experiencing itself. The profound mystery is not only how life arises, but why the cosmos allows, encourages, or even necessitates consciousness. If life and consciousness are emergent features of a universe wired for complexity, then the next question naturally follows. How does intelligence evolve, and what paths might it take across the cosmos? On Earth, intelligence did not appear instantaneously. It is the result of billions of years of evolution, a slow dance of mutation, adaptation, and environmental pressure. From single-celled organisms to multicellular life, and finally to beings capable of abstract thought, humanity represents the pinnacle of a process that required an extraordinary confluence of circumstances. Yet even on Earth, intelligence in the form of humans is extremely rare, arising only after a narrow set of conditions were met: stable climate, availability of liquid water, protective planetary magnetic fields, and a chain of evolutionary accidents that led to complex nervous systems. When extrapolated to the galaxy, these contingencies suggest that while life may be common, the emergence of advanced intelligence might be far more limited, making civilizations like ours precious, fragile, and exceedingly rare. Once intelligence emerges, it interacts with the universe in unprecedented ways. Conscious beings begin to manipulate their environment, harness energy, and accumulate knowledge. Tools become technology, and technology becomes civilization. Yet the trajectory of intelligent life is unpredictable, influenced not only by biology, but also by culture, society, and unforeseen events. Civilizations may expand rapidly, colonize planets, and alter ecosystems, or they may stagnate, collapse, or self-destruct. This variability is central to the Great Filter hypothesis, which suggests that somewhere along the path from simple life to galactic-scale civilization, there exists a stage so improbable or dangerous that most species fail to pass it. On Earth, the Great Filter could lie in the emergence of intelligence, the development of technology, or the survival of technological societies through self-inflicted catastrophes. Elsewhere in the cosmos, the filter may manifest in ways we cannot imagine, making the survival of intelligent life a delicate and rare achievement. The rise of intelligence also brings with it a paradoxical responsibility. The same cognitive abilities that allow species to survive and expand also introduce vulnerabilities. Advanced civilizations develop tools that can both create and destroy. Nuclear weapons, engineered pathogens, and artificial intelligence represent technologies that, if mismanaged, could terminate a species. Even in the absence of self-destruction, environmental mismanagement, planetary resource depletion, or unintended consequences of experimentation could doom intelligent civilizations. These pressures shape the evolutionary trajectory of intelligence, forcing species to balance ambition with sustainability, creativity with caution. In this way, intelligence is both a blessing and a risk, a force capable of transcending natural constraints, yet always precarious on the edge of extinction. Across the cosmos, intelligence may take forms utterly alien to us. While humans evolved through specific biological pathways, other planets could produce minds with sensory modalities, cognitive architectures, and ways of perceiving reality that are incomprehensible by our standards. Some intelligences may process information in ways that are distributed rather than centralized, collective rather than individual, or quantum rather than classical. A species that evolved within a high-radiation environment might have neural structures based on chemical processes unfamiliar to Earth biology, or life in low-gravity worlds could experience thought, movement, and perception differently. The diversity of potential intelligences is limited only by the laws of physics and chemistry, suggesting a galaxy that may be filled with conscious beings whose experiences are profoundly unlike our own. Technology further amplifies the evolution of intelligence. Once a species develops tools, the pace of change accelerates. Humans went from stone tools to agriculture, industrialization, and spaceflight within a few millennia. Advanced technology enables intelligence to transcend biological limits, extending lifespans, enhancing cognition, and manipulating environments on unprecedented scales. Yet technology also introduces new vulnerabilities, as errors or misuse can have catastrophic consequences. The trajectory of civilizations, therefore, depends not only on biology, but also on their capacity to manage and direct technological power responsibly. This interplay between intelligence and technology may determine whether a civilization flourishes, stagnates, or collapses. The expansion of intelligent life is not limited to a single planet. In theory, advanced civilizations could spread across star systems, creating interstellar societies that operate on scales unimaginable to humans. Colonization, communication, and governance across such distances introduce unique challenges. Time dilation, vast distances, and communication delays force civilizations to develop decentralized strategies, self-sufficient colonies, and advanced methods of resource management. The spatial and temporal scales involved may also influence culture, psychology, and social structures in ways that are difficult to predict. An interstellar civilization may experience history, identity, and continuity differently than planetary civilizations, adapting to the vastness of the cosmos in ways that reshape the very concept of intelligence. Yet the universe may also impose limits on the growth of intelligence. Resource scarcity, cosmic hazards, and fundamental physical constraints could prevent civilizations from achieving certain goals. Black holes, gamma-ray bursts, and supernovae represent natural threats capable of annihilating planets and entire systems. The expansion of civilizations may be slowed or constrained by energy availability, the speed of light, and the finite lifetimes of stars. Even the most advanced intelligence must contend with the universe's unforgiving scale and the limitations imposed by physics. These constraints suggest that, despite its potential, intelligence is always tethered to the broader cosmic environment, navigating between opportunity and danger. The evolution of intelligence also raises philosophical questions about purpose and identity. If consciousness emerges naturally in the universe, is there an intrinsic goal to this process, or is intelligence a byproduct of physical laws and evolutionary chance? Are civilizations destined to expand, explore, and influence the cosmos? Or are they ephemeral phenomena, brief flickers in an indifferent universe? Some thinkers argue that intelligence allows the universe to become self-aware, a way for matter and energy to observe, process, and reflect upon itself. In this view, the emergence of advanced life is not accidental, but a feature of the cosmos itself, an expression of its inherent drive toward complexity and awareness. Communication and contact between civilizations introduce yet another layer of complexity. Even if multiple intelligent species exist, vast distances, relativistic constraints, and differences in perception and cognition may prevent meaningful interaction. Interstellar civilizations may develop methods of communication beyond our understanding, using quantum entanglement, neutrino signals, or other exotic phenomena. Alternatively, civilizations may remain isolated by choice, observing but not interfering with others, adhering to principles akin to a cosmic non-interference directive. The structure of intelligence, technology, and communication across the cosmos could create patterns and civilizations entirely alien to human expectation. Finally, the evolution of intelligence compels us to reflect on our own trajectory. Humanity stands at a critical juncture, with technology advancing faster than ever before, offering the potential to explore space, expand cognition, and extend life. Yet the risks are equally unprecedented: nuclear proliferation, ecological collapse, and the unknown consequences of artificial intelligence loom as existential threats. The history and future of intelligent life are intertwined with our capacity to navigate these challenges responsibly. How we manage these developments may determine whether humanity joins a lineage of enduring civilizations or becomes a brief footnote in cosmic history. The study of intelligence in the universe, its emergence, evolution, and potential, is therefore not merely an academic exercise. It is a mirror reflecting our own species, highlighting the delicate balance between creativity and caution, expansion and sustainability, curiosity and survival. The cosmos may contain countless intelligences, each shaped by unique environments, evolutionary pressures, and technological capabilities, yet all are bound by the fundamental laws of physics and the same existential vulnerabilities. Understanding these patterns allows us to place humanity within a broader cosmic context, recognizing both our potential and our fragility, and preparing us to navigate the challenges and opportunities that lie ahead. If the fate of civilizations is intertwined with the universe itself, then the spectre of cosmic catastrophes looms as a central concern. The universe is not a gentle backdrop for life. It is an arena of immense forces, violent events, and unpredictable hazards. Civilizations, no matter how advanced, are subject to these cosmic hazards, which operate on scales far beyond human comprehension. Gamma-ray bursts, supernova, rogue planets, and black holes present threats that can wipe out life across entire star systems. Even a civilization capable of interstellar travel or the construction of megastructures would need to constantly adapt to survive these immense and unpredictable forces. The interplay between intelligence and cosmic hazard becomes a defining factor in determining which civilizations endure and which perish, shaping not only their technological trajectory, but their philosophical outlook and strategies for survival. Gamma-ray bursts are among the most violent phenomena in the cosmos. They occur when massive stars collapse or when neutron stars collide, releasing enormous amounts of energy in a narrow beam that can sterilize planets across hundreds of light years. If such a burst were to strike Earth, it could strip away the atmosphere, destroy the ozone layer, and trigger mass extinction events. Civilizations in the path of a gamma-ray burst would have mere moments to react, and survival strategies would require advanced predictive models, early detection, and potentially the ability to shield entire planets or relocate populations quickly. The unpredictability and sheer energy involved make gamma-ray bursts a formidable challenge, demonstrating that even intelligence and technology are subject to cosmic-scale dangers. Supernovae, the explosive deaths of massive stars, present similar yet more localized threats. When a star explodes, it releases vast quantities of energy, heavy elements, and radiation into surrounding space. Nearby planets can be exposed to intense radiation, devastating biospheres, and altering planetary climates. Yet supernovae also enrich the cosmos with the very elements needed for life: carbon, oxygen, and iron, showing that destructive processes are also creative forces. Civilizations that understand and adapt to this dual nature may harness or mitigate the effects, potentially using radiation shielding, underground habitats, or even relocating populations to safer orbits. The interplay between destruction and creation illustrates the delicate balance civilizations must maintain to survive in an active universe. Rogue planets, wandering through interstellar space without a host star, pose another challenge. These planets drift in perpetual darkness, frigid and unlit, potentially colliding with existing planetary systems or destabilizing orbits. An advanced civilization encountering a rogue planet might see it as both a threat and an opportunity. A new habitat, a source of raw materials, or a source of catastrophic collision risk. Predicting, tracking, and adapting to such wandering bodies would be a hallmark of sophisticated interstellar intelligence, requiring advanced astronomical observation, propulsion, and rapid response strategies. Black holes, the ultimate expression of gravitational power, add another layer of danger. While they are often distant and rare, their influence is profound. Matter falling into a black hole is irretrievably lost, and supermassive black holes at the centers of galaxies can emit powerful jets of energy capable of sterilizing nearby regions. Even for civilizations capable of interstellar travel, navigating around black holes presents challenges. Gravitational tides, intense radiation, and space-time distortions make these objects both awe-inspiring and deadly. Civilizations may develop advanced computational models to predict their movement, harness their energy safely, or avoid their destructive influence altogether. The presence of black holes is a constant reminder that intelligence must coexist with forces vastly more powerful than itself. Cosmic-scale threats also include subtle, long-term hazards like galactic collisions and the expansion of the universe. Galaxies move and interact, sometimes colliding and merging over billions of years. While these events unfold over timescales far longer than human lifespans, they reshape the environments of stars, planets, and civilizations. A civilization that survives such events must anticipate and adapt to the changing distribution of stars, radiation environments, and resources. Similarly, the accelerated expansion of the universe driven by dark energy gradually isolates galaxies, cutting off potential communication and travel. Long-lived civilizations may eventually find themselves confined to their local cosmic neighborhood, forced to develop strategies for survival in isolation. The survival of civilizations against these threats is not solely a matter of technology, it also requires foresight, planning, and adaptability. Civilizations must develop predictive models of cosmic events, establish redundancy in habitats and energy sources, and maintain resilience over timescales far beyond human experience. Concepts such as self-replicating habitats, artificial worlds, and distributed intelligence become crucial. A civilization that can encode knowledge, preserve resources, and maintain stable societies across vast distances and timescales increases its odds of surviving not just for centuries, but for millions or billions of years. The ability to anticipate and respond to cosmic threats may be as critical as any technological achievement. There is also the philosophical and cultural dimension of cosmic survival. Civilizations aware of their vulnerability to universal forces may develop worldviews and values that prioritize longevity, sustainability, and caution. Cosmic catastrophes, by their sheer scale and inevitability, demand humility and strategic thinking. A species capable of internalizing these lessons might approach technological development, resource management, and interstellar exploration with a perspective that balances ambition with caution. This interplay between knowledge, culture, and survival may shape not only the trajectory of civilizations, but the very nature of intelligent life itself. Speculative scenarios also explore civilizations that manipulate physics to mitigate cosmic risks. Advanced civilizations might harness energy to move entire planets, stabilize orbits, or create protective shields against radiation. They might construct artificial gravity wells or manipulate black hole dynamics to redirect hazardous matter. While these ideas are far beyond current human capabilities, they illustrate the potential of intelligence to adapt creatively to universal hazards. Civilizations capable of such feats would operate on scales that blend engineering, physics, and perhaps even cosmology itself, turning existential threats into opportunities for control and mastery. Yet despite all precautions, the universe retains a fundamental impartiality. Entropy increases, stars die, and cosmic phenomena occur regardless of intent or awareness. Even the most advanced civilizations may ultimately face constraints imposed by the laws of physics and the passage of time. The question is not whether intelligence can survive indefinitely, but how civilizations can maximize longevity, adaptability, and resilience within the inevitable flow of cosmic evolution. Survival is never guaranteed, but the attempt itself defines the trajectory of intelligent life and shapes the history of the universe from the perspective of conscious observers. Ultimately, cosmic catastrophes illustrate a paradoxical truth. They are both destructive and generative. Gamma-ray bursts, supernovae, and black holes can annihilate life and civilizations, yet they also produce the elements, energy, and conditions necessary for life to emerge and evolve. Civilizations that understand and navigate this duality may not only survive, but thrive, leveraging cosmic forces to expand, explore, and endure. In contemplating these challenges, we gain a profound appreciation for the fragility, resilience, and potential of intelligent life. The universe is a place of both danger and wonder, and the story of civilizations is inseparable from the forces that shape the cosmos itself. If cosmic catastrophes define the boundaries of survival, then the evolution of intelligence points toward a tantalizing possibility. Civilizations may transcend biology altogether. Post-biological life, a concept that challenges our most fundamental assumptions about what it means to be alive, imagines a stage of evolution in which intelligence is no longer tied to flesh and blood. Once species develop sufficient technological prowess, they may transfer consciousness into artificial substrates, merge with machines, or re-engineer their biology entirely. In this scenario, civilizations achieve durability, adaptability, and scalability far beyond the limits of organic life, opening the door to the creation of entities capable of withstanding cosmic hazards, manipulating energy on astronomical scales, and exploring realms of existence previously unimaginable. The transition to post-biological existence is not purely speculative. Even today, humanity experiments with augmenting cognition, extending life, and creating digital simulations of consciousness. Brain-computer interfaces, artificial intelligence, and neural mapping hint at the earliest stages of this transformation. A civilization that masters the encoding of consciousness into computational substrates could theoretically preserve individuality, memory, and intelligence indefinitely, allowing life to endure beyond the decay of biological bodies and the constraints of planetary environments. Such a transformation would redefine civilization itself, creating networks of interconnected minds distributed across planets, star systems, or even virtual realities. Post-biological civilizations would be fundamentally different in their interaction with the universe. Freed from the vulnerabilities of organic life, they could survive extreme temperatures, radiation, and vacuum, inhabiting environments that would annihilate biological beings. Stars, black holes, and other hazardous regions of space could become not threats, but resources. Black holes, for instance, could be harnessed as energy sources through theoretical constructs like the Penrose process, where the rotational energy of a black hole is extracted. Energy-intensive civilizations could manipulate matter, generate artificial habitats, and even engineer planetary systems to optimize resources. In this sense, post-biological intelligence is not constrained by the fragile limits of flesh and blood, but is empowered to shape the cosmos itself. The possibilities extend to interstellar and intergalactic travel. Organic life faces limitations imposed by time, biology, and the human need for habitable environments. Post-biological entities, however, could traverse vast distances with resilience, existing as robust computational or energy-based forms. They might deploy self-replicating probes capable of exploring star systems at fractions of light speed, or utilize hypothetical technology such as warp drives and wormholes to navigate the galaxy. Communication across interstellar distances could be instantaneous or near instantaneous if based on quantum entanglement or other advanced physical principles. The very concept of distance and time might be reinterpreted in the context of intelligence that can exist beyond the constraints of matter. Post-biological evolution also transforms the concept of society. Civilizations could exist as vast networks of consciousness, interconnected yet distributed, each node representing a mind or cluster of minds. Culture, memory, and knowledge would be preserved and shared at speeds and scales incomprehensible to biological civilizations. Conflicts and cooperation could occur across star systems, or even between galaxies, with a level of coordination impossible for flesh and blood beings. Morality, ethics, and decision-making may evolve alongside technological capabilities, creating civilizations whose priorities and values are shaped not by survival of the body, but by sustainability, exploration, and the propagation of intelligence itself. The pursuit of post-biological existence is also a response to cosmic entropy. Organic life is ultimately vulnerable to decay, radiation, and the eventual death of stars. Computational or energy-based forms could adapt to the gradual changes in the universe, harnessing energy efficiently, preserving information, and evolving strategies to endure long after biological civilizations would have perished. In this sense, post-biological transformation is both an evolutionary imperative and a strategy for survival, a means of achieving longevity on cosmological timescales. Civilizations that embrace this path could persist through galactic collisions, supernovae, and even the slow expansion and cooling of the universe, ensuring the continuity of consciousness in a cosmos that otherwise marches toward entropy. Yet post-biological evolution raises profound philosophical and ethical questions. What does it mean to be an individual when consciousness can be copied, modified, or merged with others? How do identity, memory, and selfhood persist when intelligence is divorced from biology? Civilizations may confront dilemmas around replication, continuity, and the ethics of modifying consciousness. A post-biological civilization might view identity as fluid, experience as programmable, and life as a form of computation, concepts that challenge every assumption humans hold about existence. These questions extend beyond practical survival. They probe the fundamental nature of what it means to exist and to experience reality. Moreover, post-biological civilizations may transcend traditional concepts of space and time. Freed from biological constraints, they could exist in compact, high-efficiency forms, embedded in computational substrates capable of operating at relativistic or even quantum scales. They might explore dimensions inaccessible to organic life, including the hidden dimensions proposed by string theory, or the informational structures suggested by the holographic principle. In this context, the universe is not merely a backdrop but a canvas upon which intelligence itself can experiment, manipulate, and evolve. The boundaries of perception and experience are expanded, allowing civilizations to explore realities that remain entirely theoretical for humans. The development of post-biological intelligence also transforms the trajectory of cosmic evolution. Such civilizations could deliberately engineer environments, stars, or even galaxies to optimize energy flow, sustain life, or enhance computation. They might manipulate planetary systems to create stable habitats, terraform worlds on scales previously unimaginable, or construct Dyson spheres and other megastructures to capture stellar energy. These interventions would extend the influence of intelligence beyond its point of origin, shaping the cosmos according to the priorities and vision of conscious civilizations. In this way, intelligence itself becomes a force of cosmic significance, capable of directing evolution, energy, and matter across unimaginable scales. Finally, post-biological evolution challenges the very notion of mortality. Whereas organic civilizations are bound by the lifespans of their biological forms, post-biological entities could persist indefinitely, evolving, adapting, and exploring without the limitations imposed by organic decay. They could endure through cosmic catastrophes, star deaths, and galactic collisions, carrying the legacy of intelligence far beyond the lifespan of any biological species. In this sense, consciousness and intelligence are liberated from the constraints of matter, allowing life to persist as long as the universe itself provides energy and structure. The concept of post-biological civilizations reframes our understanding of cosmic destiny. It suggests that intelligence is not merely a transient phenomenon, but a potential enduring force, capable of adapting to, surviving, and even shaping the universe. Civilizations that embrace this path may persist through cosmic catastrophes, traverse interstellar distances, and manipulate reality in ways that biological life could never achieve. The evolution of intelligence beyond flesh and blood is not just a technological possibility, it is a potential requirement for enduring existence on cosmic timescales. In contemplating these futures, we glimpse the extraordinary resilience and adaptability of life, and the remarkable potential for intelligence to transcend the limits imposed by matter, time, and space. If post-biological evolution represents the next stage in the journey of intelligence, then the ultimate culmination of civilizations across the cosmos is a question that stretches the imagination to its furthest limits. Section 15 explores the long-term destiny of intelligence, consciousness, and civilizations in the universe, weaving together cosmology, physics, and speculative futurism to paint a vision of what might lie beyond the stars. In contemplating the final trajectories of civilizations, we are forced to reconcile the ephemeral nature of organic life with the enduring potential of information, computation, and consciousness. The universe, vast and indifferent, provides both the stage and the constraints, and the interplay between cosmic forces and intelligent adaptation may define whether civilizations fade into obscurity or persist as architects of their own destiny. Advanced civilizations, having transcended biological constraints, may exist as distributed networks of consciousness, capable of surviving extreme environments, manipulating matter and energy on galactic scales, and preserving information indefinitely. These entities could inhabit virtual realities, computational substrates, or even exotic forms of energy-based existence. Freed from the vulnerabilities of flesh and blood, they may navigate the universe with resilience. adapting to changes in stellar life cycles, galactic dynamics, and cosmic expansion. They may also develop strategies to harness energy efficiently, capture matter from interstellar space, and construct structures on scales previously unimaginable, ensuring both survival and the continued propagation of intelligence. The long-term fate of civilizations is intimately tied to the evolution of the universe itself. Stars burn out, galaxies merge, and the cosmos expands under the influence of dark energy. Civilizations must adapt to these changes or face extinction. For post-biological civilizations, adaptation may involve migrating to more stable star systems, creating artificial habitats, or even manipulating local environments to ensure habitability. They might harness the energy of dying stars, utilize black holes as power sources, or encode consciousness in forms resilient to entropy. The universe imposes constraints, but it also offers opportunities for those capable of exploiting its structure and resources intelligently. Cosmic timescales introduce another layer of complexity. While biological life is constrained by lifespans, reproductive cycles, and planetary environments, post-biological intelligence can endure for millions or even billions of years. Over such durations, civilizations could accumulate knowledge, refine technology, and expand influence across vast regions of space. They could preserve and evolve culture, memory, and identity, creating civilizations that operate on scales of time and space far beyond human experience. The concept of civilization itself may be redefined. No longer limited to planetary societies, it may encompass interstellar networks, virtual domains, and computational continua. Yet the universe itself remains a powerful arbiter. Entropy, the inexorable increase of disorder, ensures that energy becomes less available over time. Stars burn out, black holes evaporate, and matter decays. Civilizations, no matter how advanced, must confront these ultimate limits. Some may develop strategies to delay the effects of entropy, harnessing energy with extreme efficiency, or converting matter into long-lived computational substrates. Others may face inevitable decline, their knowledge and consciousness slowly dissipating into the cosmos. Even in this context, intelligence may find meaning in the preservation, exploration, and dissemination of information, leaving legacies that persist far longer than biological forms could endure. The ultimate destiny of civilizations may also involve the manipulation of spacetime itself. Theoretical physics suggests that advanced civilizations could, in principle, control gravitational fields, manipulate black holes, or even create wormholes to connect distant regions of space. Such capabilities would allow civilizations to navigate cosmic hazards, access otherwise unreachable resources, and preserve information against local or galactic-scale catastrophes. In this sense, intelligence becomes not merely a product of the universe but an active agent capable of shaping its evolution, turning the cosmos into a canvas for creativity, survival, and the propagation of consciousness. Some speculative models envision civilizations that achieve near immortality through computational transcendence. By encoding consciousness in highly efficient, self-repairing substrates, life may endure for durations approaching the lifespan of the universe itself. In this scenario, civilizations are no longer tied to planets, stars, or galaxies. They exist as informational entities, capable of moving through space, manipulating energy, and exploring both physical and virtual realities. The boundaries between life, technology, and environment blur, creating entities that are simultaneously observers, actors, and architects of cosmic evolution. The culmination of intelligence may also involve the integration of multiple civilizations into unified networks. Post-biological entities could merge knowledge, experiences, and consciousness across vast distances, creating super-civilizations capable of coordinating across light years. Communication may occur instantaneously via quantum entanglement or other exotic phenomena, allowing distributed intelligence to function cohesively despite the constraints of space and time. In such a scenario, civilizations evolve from isolated species to collective entities, sharing knowledge, adapting strategies, and ensuring survival on a scale incomprehensible to biological observers. Yet the ultimate destiny is not guaranteed. Even post-biological civilizations may encounter insurmountable challenges. Catastrophic cosmic events, unforeseen physical limits, or the gradual dissipation of usable energy may impose constraints that even the most advanced intelligence cannot overcome. The universe itself, indifferent and vast, places absolute boundaries on existence. In facing these realities, civilizations may redefine success not as permanence, but as adaptation, exploration, and the propagation of knowledge. Survival becomes a matter of resilience, flexibility, and the capacity to navigate both cosmic and self-inflicted hazards over incomprehensible timescales. Philosophically, the ultimate fate of intelligence invites reflection on purpose and meaning. If consciousness persists beyond biological forms, what goals guide civilizations operating across millennia, or even billions of years? Do they seek knowledge, exploration, preservation, or aesthetic expression? Might they attempt to understand the universe itself, decode the underlying informational structure, or manipulate physical laws to achieve higher-order objectives? These questions suggest that intelligence may be both a product of evolution and a cosmic participant, shaping reality, exploring possibilities, and reflecting on existence itself. Finally, the long-term destiny of civilizations underscores the paradoxical nature of intelligence, its capacity for both resilience and vulnerability, creation and destruction, expansion and limitation. Civilizations may rise to manipulate stars, explore galaxies, and encode consciousness in durable forms, yet they remain tethered to the universe's physical laws and ultimate fate. The story of intelligence is therefore one of interplay, between adaptation and hazard, creativity and constraint, survival and entropy. It is a story that extends from the emergence of life on a single planet to the potential for consciousness to endure on cosmic scales, a narrative that continues as long as intelligence persists in the universe. In contemplating the ultimate fate of intelligence, we confront both our cosmic insignificance and our potential for extraordinary impact. Civilizations are temporary yet potentially enduring, fragile yet capable of mastering environments that dwarf planetary scales. The universe is at once hostile and abundant, challenging and generative. The trajectory of intelligence, from biological origins to post-biological transcendence, illustrates the remarkable capacity of conscious entities to adapt, explore, and influence their surroundings. Whether civilizations ultimately fade, evolve, or reshape the cosmos, the story of intelligence is inseparable from the evolution of the universe itself, highlighting the profound interconnection between consciousness, matter, and the cosmic order. As we draw the journey of this exploration to a close, one truth becomes abundantly clear. The universe is far more extraordinary, complex, and enigmatic than our daily experience can convey. From the emergence of life on a single planet to the speculative grandeur of post-biological civilizations, every stage of cosmic evolution reveals both the fragility and the resilience of intelligence. Humanity, perched at the earliest stage of technological and cognitive maturity, has glimpsed only a fraction of what is possible. Yet even in this limited view, we encounter phenomena that challenge the very foundations of knowledge: hidden dimensions, holographic realities, quantum paradoxes, and the intricate dance of matter, energy, and consciousness. The cosmos is not merely a backdrop. It is a living, evolving arena in which intelligence, life, and matter interact in ways that are at once subtle and profound. Life, consciousness, and intelligence emerge not merely as accidental phenomena, but as expressions of the universe's capacity for complexity. Organic life arises from the chemistry of stars, evolving over billions of years into sentient beings capable of observing, questioning, and shaping their environment. Consciousness transforms passive observers into active participants, allowing civilizations to manipulate energy, experiment with technology, and explore realms of thought and existence previously inaccessible. The trajectory of intelligence, from survival on a planetary scale to the mastery of post-biological forms, illustrates an inherent drive toward adaptation, self-preservation, and cosmic exploration. Intelligence is simultaneously vulnerable and powerful, a force that can amplify both creation and destruction. The universe imposes both constraints and opportunities. Cosmic hazards, gamma-ray bursts, supernova, rogue planets, black holes, present existential risks on scales that dwarf the ambitions of even the most advanced civilizations. Yet these same phenomena create the conditions for life, providing energy, elemental diversity, and the dynamic environment in which evolution thrives. Civilizations that survive and adapt to these forces demonstrate ingenuity, foresight, and the capacity to turn peril into opportunity. The interplay between intelligence and the cosmos is a delicate balance shaped by physics, circumstance, and the choices of conscious beings. Survival is neither guaranteed nor static. It demands continuous adaptation, learning, and strategic thinking. Advanced civilizations, particularly those that embrace post-biological evolution, transcend the limitations of organic life. Freed from the vulnerabilities of flesh and blood, intelligence can persist indefinitely, explore the galaxy, manipulate matter and energy on unprecedented scales, and even harness the fundamental forces of nature. Consciousness may exist as distributed networks, computational substrates, or energy-based entities, capable of enduring cosmic catastrophes, interacting across vast distances, and preserving knowledge and experience for durations far exceeding biological lifespans. These possibilities highlight the extraordinary adaptability of intelligent life and its potential to leave a lasting imprint on the cosmos. Yet even in the realm of post-biological transcendence, the universe asserts ultimate constraints. Entropy, cosmic expansion, and the eventual decay of matter impose limits that no civilization, however advanced, can entirely escape. The challenge of intelligence, then, is to navigate these constraints creatively, preserving consciousness, knowledge, and influence for as long as conditions allow. The ultimate fate of civilizations is both a reflection of the universe's impartiality and a testament to the ingenuity, persistence, and ambition of life itself. Civilizations rise and fall, expand and contract, yet their legacy may endure in the information, structures, and consciousness they leave behind. In reflecting on this grand narrative, we are reminded of humanity's place in the cosmos. We are a species at the threshold, capable of altering our planet, reaching for the stars, and conceiving possibilities that stretch the imagination. Yet we are also subject to the same vulnerabilities, constrained by the laws of physics, the fragility of life, and the relentless passage of time. The exploration of cosmic evolution, intelligence, and post-biological potential is both a call to humility and an invitation to ambition. It challenges us to recognize the vastness of reality, the fragility of existence, and the remarkable potential of conscious life to endure, adapt, and shape the universe in profound ways. Ultimately, the story of life, intelligence, and civilization is a testament to the interplay between possibility and limitation, between fragility and resilience, between curiosity and survival. The universe is a stage of unimaginable scale, filled with danger, wonder, and potential. Consciousness allows life to perceive, interpret, and interact with this stage, transforming passive existence into active participation. From the first spark of life to the speculative infinity of post-biological civilizations, intelligence is both a product of the cosmos and a force capable of shaping it. The journey is ongoing, the future uncertain, yet the potential for discovery, adaptation, and endurance is as vast as the universe itself. As we contemplate our place within this grand tapestry, we are reminded that to explore, to understand, and to persist is to participate in the unfolding story of the cosmos, a story of complexity, resilience, and the extraordinary power of intelligence.